thank you very much for joining us here today. You are in the right place if you are here for part 3 of our high-speed webinar series. Part 3 will focus on the PCB structure in addition to tying some loose ends. Our presenter today is Sean Kelly, who is an expert in high-speed design. Now, before we begin, I want to let you know that we will have time for questions today, so please feel free to write them down in the questions panel of your GoToMeeting panel. And we just simply ask that you be specific since the questions will not be addressed until the end of the presentation. So with that, I will turn the microphone over to our presenter, Sean Kelly.
Welcome everybody to today's presentation. Thank you for taking time out of your busy schedule, and let's get started. So the purpose of this webinar series is to give practical understanding and solutions relative to high-speed designs. In part 1 of this 3-part series, we discussed relative permittivity, commonly known as dielectric constant, and the loss tangent. In part 2, we talked about PCB routing concepts and issues, and if you would like to watch those videos, please feel free to contact us and we will get those links to you. In today's webinar, which will sum up all the data that we've talked about so far, we're going to talk about interconnects, PCB material issues, selection, stack-up recommendations. But before we get started, one of the common questions that I've seen over the years is, what constitutes high-speed design? So I'd like to know your position on this as far as what you think high-speed design means to you. Okay, interesting. Anything over 1 gigahertz got 32%, 39% said depends. Very good, actually. So let's go on to the rest of this. So in my perspective, it depends rules the roost, because there's 2 ways to look at the answer. It depends on whether you're looking at harmonics or you're looking at rise time. So you can have a low frequency with fast time, rise time, and that can still be considered high speed. The general rules to follow is to rise times faster than 1 nanoseconds, then there are going to be high frequencies to be concerned about. If the signal's fundamental frequency approaches 1 gigahertz, then automatically there are higher order harmonics to be concerned about. That kind of goes to what we talked about in the first 2 parts of this series, is the 3rd and 5th harmonic of a square wave concept as to what frequency content to be concerned about. So when we're talking about rise time calculations to determine frequencies of concerns, if you're looking at lower clock speeds, you're going to ultimately want to know what higher order frequencies you want to be worried about that are creating that sharp edge. This is going to be called a maximum pulse frequency. Now I'm going to talk about this K value and how it's used, but just for now, understand K equals 0.5 is good for slow signals with fast edges. And if you'll notice here, K is in this equation for this maximum pulse frequency. Now I've created a table over here for you to see different values of K. Now Rick Hartley would suggest that you use a K of 0.5. Now, understanding that I am thinking that even though most people talk about a rise time as 10% to 90%, for ease of calculation, I just said from 0 to 100% is the rise time. The total period is going to be 4 times that. So you basically have 166.7, 166.7, same here, and same here. That's 1 period. When you do that, you can see that the frequency of concern here of the main period is 1.5 gigahertz. When you take this equation and you use the K of 0.5, then Rick would say that your frequency max would be 3 gigahertz. Now if we're going to go to rise time of 100 picoseconds and then 40 picoseconds, you can see consequently your main frequency of concern even goes higher. Now this is fine if you're dealing with very slow clocks, because this is the dominant portion of your frequencies of concern. Lightwave comes up with some other concepts, and it's a great article, and I'll put a link here for you. But they're saying that you should use a K of 0.64. And if, in my estimation, if you're using low clock frequencies and you're worried about rise time being the dominant feature, then use 0.64. You can see the consequence up here is the greater frequencies of concern are even higher. Now, going back to the frequency content of just a square wave at those same frequencies, you can see that the fifth harmonic rule shows even a greater frequencies of concern. So it just kind of depends on if you're dealing with a harmonic issue or are you dealing with a rise time issue as your dominant thought of high-speed design. Now, in the previous part of this series, we talked about a reference plane. Some people refer to it as a ground plane. Sometimes people refer to it as a return path. But in my estimation, that's not the best way to understand it, because this reference plane is half of the field system. The key is to minimize disruption of the field along the propagation path as it relates to the signal path and the reference. You've got to treat them simultaneously. For signal propagation, you got to think about the charges moving is basically the same thing as the field propagating. Don't separate the two, and you'll see more of this later on as to why. If you hinder either, the net effect is to reduce your signal integrity. The copper's characteristics is going to hinder the charge movement, that is the electrons moving through the copper, and the dielectric is going to hinder the field movement. We talked about that in the previous part of the webinar. The total solution is going to encompass dealing with both areas. Now, with that in mind, I'd like you to tell me if you saw this 2x17 header and had to wire it up in your schematic, how many of you all would route this in this format, with G being ground, S being a signal, and P being power? Wow, that's awesome news. There's a lot of smart people out there. So 56% said never. That's good. If you have voted sometimes or even fairly typical, don't feel too bad. There's a lot of people that make this mistake. And I'm going to hope to help you to understand why this is a bad idea. From previous polling questions in the previous webinars, many of you all are concerned about getting signals on and off the PCB. So here's a little chart over here on the right that can show you conventional connector pin assignment. When you don't understand why the reference plane is important and you route like we did in the previous question, you can see this is very poor because the reference planes, the ground and the power, are so far away from your signal planes. Even better would be for you to surround any signals with a ground. Even if you used a power, it'd still be better. So you have a signal, each signal line has a reference to a power plane. Even better would be to have a signal to a ground and sharing the ground and power plane reference. The best scenario is if you have each signal has its own reference. Then there's no worry about crosstalk. And that's why Rick puts in here that you have a ground and a signal to power, just like that. And so every signal has its own reference. So why does this issue keep coming up? It's because proper referencing for the signal conductors is ignored. Now here's a newer connector made by IPEX. These people really gave a lot of thought into how to make sure their connector did not inhibit signal maintaining integrity. So even though it's a coax type of connector, what they did here should apply to all connectors anytime you have high frequency concerns. If you'll notice here in the coax, they have their reference plane being connected through one signal or one part of the connector down here and then connected to the circuit board. At the same time, they have their center conductor going to another part of the connector, but physically they are referenced to each other. So they're trying to maintain integrity of that physical dimension between the signal and the reference plane. Now, we can extend this to packaging for your ICs. Here are some poor examples of packaging that has been actually implemented by manufacturers. Now, let me mention a little bit of history. If you all are as old as I am, you may remember that a lot of the 14 and 16 pin SOIC type packages would have power and ground on opposing corners of the IC package. That's because most of those packages, they weren't worried about high-speed designs or sharp edges. They were more worried about compatibility. So they would put power on pin 1 in one corner, and then you would have ground on pin 8 in the other corner, or something similar to that. In this example, you'll notice they've got ground here, power here. They don't have another ground until way down here. So any of these IOs coming out of this package, they don't have a nice ground reference. Here's a BGA part. It's even worse. Their ground is dead set in the middle of the part, and all these IOs out here on the end don't have a reference to the ground. Now, this package example demonstrates a need for a signal to have its own reference. If you notice here on the right, there are many regions devoid of returns. The X's are your signals coming out of the part, but yet the little colored circles are your reference planes. And you'll notice there's some great distances between the signals and the reference. It makes for a very odd impedance situation there. Then if you notice, when the manufacturer said, well, we want to maintain signal integrity through as the part leaves the die out to the board, then they dispersed the ground and power pins. So now it's not perfect, but it is much better. So they had all these IOs have a light pink or dark red ground power reference as their signal reference. So the key here is you want to look for a part that has power and ground pins or pads evenly distributed. If you're going to go buy an FPGA and put it on your board, just be aware that if the pin out is not such that you have good references, you can expect either EMI issues and or impedance mismatch problems. The reference planes created that return path people talk about. Now, I have a situation here that I want you to take a look at. We have a microstrip on the top. That's this dotted line right here with the ground plane underneath it. Nothing fancy, just a normal microstrip. And this professor did a study. And what he wanted to find out is which one of these cases created the worst radiation. In other words, when you're radiating signals, you don't have energy left in your as much left in your signal to create a good signal recreation at the load. So look at these 4 situations, and I want you to rate them as increasing order of radiation tendency. Okay, so the answer is C, actually, and it is interesting that there was a greater percentage that said E. 2, 4, 3, then 1. So when you're looking at this, the least amount of radiation is going to be created by just a normal microstrip. Most of the fields will be contained between the microstrip and the ground reference. In case 3, there's not a whole lot of difference. The microstrip is still over a uniform ground plane directly underneath it. Case 4, there is going to be some minor radiation created by the holes in this dielectric or in the ground plane underneath this. But the interesting thing is case 2 creates a major radiation problem. The elongated path for the field around the slot induced fields in that slot. So when you're looking at the radiation, then you can see that case 1 and case 3, that's these 2 on the left, were really very well behaved. In other words, they didn't have a large amount of electric field that wasn't, radiating. Now, when you went to case 4, which is here in the bottom right-hand corner, this hole in the copper did in fact create a little bit of a problem, because ultimately the fields would have to stretch around and go around the edge of this little square in order to catch up to the other side. But the problem really came in with case 2, because in case 2, which is up here, when the field is trying to propagate along this path and it hits this open slot, the field has to distend itself all the way around this edge and come back over here. Case 2 is actually an example of a slot line antenna. If you're trying to make an antenna and radiate energy, you would use something similar to this. The key here is to remember that energy radiated is energy not available to reconstruct the proper shape of the signal at the load. When we're going to look at the E fields in each one of these cases to help you to understand, you can see that they're contained fairly uniformly in cases 1, 3, and 4. But in case 2, the field stretched around the slot, and you can see all this energy on the slot itself. The energy got coupled into the slot. So why is this important, and how does it relate to interconnects? Ultimately, deforming the field is going to ultimately negatively impact your signal integrity. Now, next part of the webinar, PCB material selection. It's a common question. Ultimately, it's going to break down into concept of loss. In the previous webinars, we talked about dielectric losses as they relate to the dielectric constant and the loss tangent. Normally, you want both of those to be as low as possible. The second part is the conductive loss, and we're going to talk about that today. Frequency is a factor. The higher the frequency, the more the conductor plays a part and can even dominate this decision. In that, I want you to consider skin effect, conductor roughness, and then consistency of the dielectric. Now, most of us are at least somewhat familiar with skin effect, so I'm not going to go into a whole lot of detail about how to calculate it. But just understand the skin depth has an inverse relationship to frequency. The higher the frequency, the smaller the skin depth. But just how significant is it in high-speed design? So at its root understanding, skin depth is defined as a depth below the surface of the conductor at which the current density has fallen to 1 over E. That is about 37% of your conductor current. At the surface, conductivity is 100%. At 1 skin depth, that conductivity is decreased to 36.8%. Basically, that means 63.2% of your overall current is in that 1 skin depth of the conductor. At 2 skin depths, you see it drops off to 13.5, 3 is 5, 4 is 1.8, and at 5, you pretty much have covered all of your current. If you have 5 skin depths of metal, you have all your current, and that is unless you mess up the surface. So when we talk about skin depths, let's give some numbers to it. So what I want to do is give you a visual depiction of various single skin depths based on frequency. So if this was a side view of a microstrip piece of copper, at DC, we would all agree that the electrons are evenly dispersed through the copper. But when you get to 100 megahertz, which is this line right here, the skin depth is only 0.257 mils, or 6.5 microns. And if you're dealing with 1.4 mils worth of copper, then you're talking about 18% of the thickness of the copper has 63% of that electrons moving. When you go to 1 gigahertz, you see that that 1 skin depth has dropped to only about 2 microns. When you go to 10 gigahertz, it's dropped down to 0.65 microns. So at 10 gigahertz, 63.2% of your electrons are moving and only 2% of your conductor. Now, this is an example of a uniformly distributed E field. Now, let's consider the density due to an E field influence. Because keep in mind, this uniformly distributed E field would be as if this was a single conductor sitting out in in air with no reference plane around it. It would be just all the E fields would be distributed equally. But when you have a microstrip, we all know that the E fields are not distributed evenly. In fact, most of the E field exists between the microstrip and the reference plane, and so therefore, most charges are going to be on the bottom of this diagram. Now, conductor roughness is not something that most of the PCB engineers are concerned with, especially if they've never done high-speed design. But as rise times and frequencies increased over the years, the S21, which we've talked about in the past, is a number that shows loss from port 1 getting to port 2, showed a dramatic loss, and that could not be accounted for, as well as other impacts. So studies were done to find that root cause, and they found out that conductor roughness was the culprit. So PCB copper foil today is typically fabricated in two different ways: electrodeposited, which you'll see in my diagrams or presentation labeled ED, or rolled annealed. And it says, I mean, it's exactly the way it sounds. You either electrodeposit it or you run copper through a roll and squish it to the thickness you need it. The thing here is to understand rolled is better. If you don't get anything out of this seminar except for this, remember, rolled is better. Rolled annealed has less loss. So if you'll notice, during these two tests, the first one being 20 mil substrate, that's going to be your purple and green line over here. And you'll notice that with the rolled copper, your S21 was less than it would be with the electrodeposited copper. Now the interesting thing is when you go to a 5 mil test, that the test is even more dramatic of an impact. So with a 5 mil substrate, you can see that if you go with electrodeposited, you have quite a significantly more loss at a given frequency than you would with rolled copper. Here's another test that was done. They kept the substrate the same, and they changed only the foil and the roughness. So if you'll notice here, this is the effect on the dielectric constant itself. So if you'll notice here, this electrodeposited copper, depending upon whether or not the profile, which we're going to talk more about as it relates to RMS, that's how big the valleys and the peaks and valleys are. So this is a very rough signal, or very rough copper. This is a less rough copper. These are two rolled pieces of copper. And again, this is an even smoother piece of copper. So the dielectric constant is the smallest and actually will be closest to what would be referred to as the bulk dielectric materials property. The higher RMS causes a higher effective dielectric constant. And the interesting thing about it is if you start doing any modeling in electromagnetic simulators, you'll need to understand that this conductor roughness will change what dielectric constant you want to use in your simulations. So a question, why does a thinner dielectric cause a greater impact on the S21 for a given roughness? All right, so we had B got 34%, C got 24%, and D got 35%. Good, well the answer is in fact D. The stronger E fields are going to pull the charges closer to the surface. If you go back to what we were talking about before, and this is a very thin piece of copper microstrip, when you're thinking about all the electrons and their density in this copper, most of them are going to be on the very bottom, that is that part that is glued to the substrate. Not only is it going to be a majority on the bottom, but they're actually going to collect more in the corners. The thinner this dielectric is, the closer the positive and negative charges are, therefore the E field is going to be stronger. That attraction between the positive and negative is going to be greater. So whatever electrons were in the top of the copper will be pulled down even more toward the bottom of the copper. So that was why the answer D was correct. Now, I want you to understand that the current density in the reference plane is also greatest right under the microstrip. So if you were to look at the charge distribution along this plane, you would see that it follows a tendency of this red line here, that the greatest charge density is right underneath the microstrip. And we already talked about the greatest concentration is in the corners of the microstrip. Therefore, the vast majority of your current is going to be subject to the influence of surface roughness. Now this term RMS is used to describe the RMS value of the conductor roughness. This is called a profile. So you'll hear me using this term profile quite a bit. On electrodeposited profiles, they typically run somewhere between 1 and 3 microns. For rolled, sometimes they're less than 0.4, but 0.4 to 0.5 is pretty typical. The initial models of these profiles took on a sawtooth shape. It was called the Hammerstedt and Jensen model. The problem with this model is, as we got higher and higher frequencies, the model wasn't able to predict properly the losses involved. And what they come to find out is it's because the model had the loss saturating at a value of 2, when in fact it could go quite a bit higher. So in recent years, a different model was created called the Hooray model. It gained popularity due to the continually increasing data rates need for better modeling accuracy. The model is based on a non-uniform distribution of spherical shapes resembling snowballs. If you look over here, you'll see all these peaks and valleys. There's nothing uniform about it whatsoever. And you even have these little snowball-looking things on top of it. This picture was created by a scanning electron microscope. So if you think about, okay, are the charges moving along this path perpendicular to what you see these mountains and valleys? The electrons don't just ignore these. They actually go up and down, and they follow that surface. And that's why you end up creating extra losses the higher frequency you go. The rule of thumb for surface roughness is your effective dielectric constant is going to increase as your profile increases for any given substrate. As the frequency increases, aka the skin effect, your inductance is also going to increase because of the way the charges behave relative to those peaks and valleys. Interesting enough, it also is going to change your propagation. It's going to slow it down. Because ultimately, if you remember back from our previous webinars, we talked about velocity of propagation. It's directly related to the dielectric constant. If the higher the dielectric constant you have, the slower the wave propagates through the dielectric. Since the roughness, as it increases, is going to increase the effective dielectric constant, it slows the propagation of your signal. This causes an S21 phase delay. The rougher surfaces exacerbate all these effects. So concluding thoughts. As you need frequencies higher and higher to propagate and thinner dielectrics because you want a greater stack up, the greater your need is to take surface roughness into consideration. There's a great article written by John Conrad at Rogers Corporation, Choosing Copper Foils for High Frequency PCBs. It's readily available. You can search on it on the internet. It's a great primer for this and does a great job of explaining the details. But Rogers also created a tool called MWI 2017. It's a calculator you can download, and it will show you things such as when you pick a material, it'll show you surface roughness. you can go back and forth and pick different materials and notice that the surface roughness changes, and then you can see the change in your effective dielectric constant, and you can see how the total loss is going to change per inch. Now, I will tell you that 4350B material has been used for quite a while now as a low loss material. But in my opinion, what Rogers has figured out not too long ago was this surface roughness was even more of a concern than what they thought of. Then they actually created this low pro. And this low pro is basically a low profile type of material where they've gone to extensive ability to make the material super smooth. In fact, the low pro is what I did here, and it was 0.8 microns. If you go to the normal 4350, I remember correctly, that jumps up to 2.8. So, you know, you're talking about a third the roughness. So a question here, why is rolled copper foil better for high-speed design? Awesome. There are a lot of people out there listening to me. So the answer is E, because it has such a low profile. I want you to think of the substrate also as part of the problem you could have to deal with, especially on differential pairs. And this next problem we're going to talk about is created because of a term called weave. If you'll notice down here, there are FR4 type of materials will have this weave in there with a resin in between the holes. And if you remember from a previous webinar, we talked about the material that makes up the substrate has a different dielectric constant than the resin itself. If we have two differential signal lines sitting on this weave, it possibly could be sitting on two completely different ERs, or dielectric constants. The results are going to be that one signal line is going to arrive differently than the other, and there'll be an impedance mismatch. Now, keep in mind, when we talked about differential pairs before, we talked about anytime you're routing a differential pair, you're trying to keep your fields symmetrical as they propagate along the path. So anytime you change layers, you want to try and keep your vias set up so that all the field stays relative to each other as it propagates and changes layers. Well, it's the same thing when you're on this type of weave. If you have one of these traces that's sitting over a majority of resin, where the other one is sitting over a majority of glass, then the one signal is going to travel slower than the other, so you're distorting the E field going between the two. The interesting thing is, if you have a tight weave, then the properties are going to average out over very short distances. So it's not quite as a problem if you're making short runs. But you don't want to spec 106 or 1080 glass if you can help it. The other thing you want to do is be very cognizant of how long your differential pairs are. And if you're going to route them in very long straight lines, you definitely want to be worried about the weave. So obviously you may have to route straight lines or long lines anyhow, but there's other ways to deal with that. But if you got to do it, you can spec flat, tightly woven glass such as the Park-Nelco 3313 or the Sola 1067, 1086 class. But keep in mind the weave is always on axis. In other words, if you're thinking about routing in the X and Y axis, well, your weave is also going to be on the X and Y axis because that's the way that it's manufactured. So one of the things you can do is route on 45-degree angles. Well, that's not always the best way to do it. Your density may be such that it precludes from using a lot of 45-degree angles. So one of the ways you can deal with this and just route your board like you normally would is actually ask the fabricator to put a bias on the board. So what they do is they put the board in the machine and they tilt it basically. They skew it 10 to 15 degrees. And so even though your differential pairs are running parallel to the X and Y axis, the board is not parallel to the X and Y axis. Now, stack-up recommendations. This is another very common question we have is what is a good stack up? In my opinion, good high-speed design stack-ups come down to one key concept. It's the same concept we've been talking about in all three of the series. It's the same concept for connectors. Make sure your signals have reference to allow proper field movement. Whether it's a ground or power plane, you need to make sure you have that reference. One additional thing to consider, don't have your signal layers share reference planes, if at all possible. Here's an example of sharing reference planes. Again, here's another example that Rick Hartley has given me, is an example of 6-layer design to avoid. And you see this all the time where you'll have internal ground and power, and they think, oh, this is great. I have a ground and power that's really close. It may be on a 2 mil substrate, so I've got all this internal capacitance created to minimize my ground bounce and to create decoupling. And so what they do is they put the signal layers on the outside. But what they don't think about is on high-speed designs, this is really problematic because now you've got this signal layer on layer 1 and layer 6 that are having to go through layer 2 and layer 5 in order to get to a reference plane. This increases the likelihood of crosstalk. The main problem is, again, you're stretching the field lines, increasing the possibilities of EMI. Now here's examples of 4-layer board. You might want to use this. As long as you create proper vias in the grounding, this is a good method. What Rick would tell you is that you want to try and create as many fills as possible anywhere you can in order to create references. It's interesting that I think most of us engineers, we don't understand how easily these signals will use a power plane as a reference. Even when we don't intend it to, it will. Here's another example of a 6-layer. In this situation, again, there's always pores put into the ground layer, around the signal layers. Now, in this situation over here, you'll notice, oh, well, wait a minute, doesn't this contradict what you just said 2 slides ago? Not really. We're talking about statistics here. If you have a very short signal, it can use the ground pore here because statistically speaking, there's probably going to be a ground underneath this very short signal. So it's not the ideal. So this would be better. Now here's even better examples. Again, every signal has a reference. Here's another example of an 8-layer board. Notice though that B and C is better than A due to copper pores. So when you're dealing with high-speed designs and you're trying to minimize your EMI, you want to contain your fields. And if you contain your fields by keeping pores available, that's the way to do it. And so therefore B and C is better. Well, that concludes today's presentation. If you don't mind, take a second and give me your input as to how you enjoyed the materials presentation.
Well, again, thank you very much for joining us here today. We are 9.Connects, and we know that you're here for a reason, right? The topics of this nature are very, very important to you. That high-speed design is indeed the future, and that high-speed design certainly requires a knowledge kind of above and beyond just the simple intuitive concepts. But the big thing is we want to make sure you understand that you're not out there on your own, that we're here to help you here at 9.Connects. So what do we do here at 9.Connects? Well, it's PCB knowledge that we sell. And we sell it in different forms. You can see all of our action verbs over here. We do training, coaching, consulting, design, and layout. So anything that has to do with the printed circuit board, we are there to assist you with it. Okay? But more importantly, it's about the topics as well. So topics such as high-speed design, that's why we have Sean come out here and provide these webinars to you so that you can see that we do have this knowledge in-house. We also have knowledge in RF and in power. We also have quite a bit of knowledge in design for manufacturing. We see that's a really large issue in our industry. A lot of us went through academia. We weren't necessarily taught on PCB design, and we're learning it through experience and sometimes through the school of hard knocks, so to speak. And in fact, as a matter of fact, we also have a 3-day training called the PCB Fundamentals to address this specific issue. So if you're interested in that, certainly check out our website, and we'll be more than happy to provide you more information. We are also library experts, not just in terms of creating library components, but also library methodologies. We've spent a lot of time researching them and understanding where companies struggle with them. And also, believe it or not, we also have a large presence in the mechanical aspects. We have a number of our guys who are not only very good at PCB, but we're also very good in the mechanical side of things as well. And as a matter of fact, we're seeing more and more of a need for us and even the industry in general to get to what we'll call the mechatronics aspect of design, where it's not just the PCB aspect, but we also have to take in very much the mechanical level and also the system level, in addition to the manufacturing level as well. So doing PCB design is just simply no longer drawing schematics and just simply getting through a layout that works. There's a lot of other factors that are involved in that and much, much more. So the short of it is that your success really is our success. And we want you to get beyond your technical hurdles. We want to confront those technical hurdles with you. So if there's things that you're just not comfortable with, a lot of people are looking into USB or high-speed USB. They don't know, they're not sure how to implement it, or maybe they want to go wireless and they're not sure how to implement it. We can certainly assist you with that as well. But in the end, whether or not you are you're trying to just get it done by yourself and just need a push, or if you want us to just basically take the design, whatever level of assistance that you need, we're more than happy to assist you with that. So obviously, we just only had a few minutes to introduce ourselves. Do check us out at 9.connects.com. We did really set it up to be a source of information for you out there. Obviously, we do have our products and their services that we'd like to provide to you, but there's enough information out there as well, such as our videos and our commentary, that hopefully will guide you along as well. Thank you very much, and have a great day.